The moon is already leaving. Right now, tonight, it is drifting about an inch and a half farther away from Earth every single year. That sounds harmless. It is not. Because if that drift accelerated, if the moon slowly but steadily pulled away over thousands and then millions of years, Earth would become a fundamentally different planet. Not dramatically different overnight. Worse than that. Quietly, systematically, catastrophically different. Let's walk through exactly what would happen, step by step, starting the moment the drift picks up speed. The first thing you would lose is the tides. Not immediately, not all at once, but gradually, the tidal range would shrink. Right now, the moon's gravity pulls Earth's oceans into two slight bulges, one facing the moon, one facing away. And as Earth rotates beneath them, coastlines experience high and low tides. Those tides are not just scenery, they are biological engines. Tidal zones are among the most productive ecosystems on the planet. Twice a day, seawater floods shallow coastal flats and then retreats. And in that rhythm, enormous quantities of nutrients get churned, distributed, and recycled. Kelp forests, mangroves, oyster beds, crab nurseries, bird feeding grounds, all of it depends on that daily push and pull. As the moon retreats and tidal forces weaken, those intertidal zones would shrink. The mixing would slow. Coastal ecosystems that have been tuned to tidal cycles for hundreds of millions of years would begin to lose their rhythm, which is a polite way of saying they would start collapsing. Now here is where it gets more interesting, and by interesting, I mean deeply unsettling. The tides do not just affect the oceans, they also act as a brake on Earth's rotation. Every time the ocean tidal bulge gets dragged slightly behind the moon due to friction, it pulls back on Earth's spin, ever so gently slowing it down. This is actually why our days are getting longer, 1 second every 50,000 years or so, which is not a crisis, but is technically true. Now reverse that. As the moon drifts away, that braking force weakens. Earth starts spinning a little faster, not dramatically at first, but over thousands of years, the days get shorter. We are talking about a planet that once had days lasting only 6 hours, back when it was young and the moon was much closer. Move the moon out far enough, and Earth starts creeping back toward that faster rotation. A shorter day means more powerful winds. Earth's atmosphere responds to rotation through a phenomenon called the Coriolis effect, the force that curves wind patterns and drives the circulation of weather systems. Faster spin means stronger Coriolis, which means more intense and more persistent storm systems. You think hurricane season is inconvenient now. A faster spinning Earth would generate atmospheric circulation patterns that are more violent, more chaotic, and less predictable. Weather as a stable background feature of civilization starts to degrade. Agriculture, which requires some baseline of seasonal reliability, begins to struggle. And that brings us to the seasons, because the moon's influence on Earth's axial tilt is the part of this story that most people have never heard, and it is arguably the most important one. Earth is currently tilted at about 23.5 degrees relative to its orbit around the sun. That tilt is what gives us seasons. It is also, broadly speaking, why Earth has been habitable for billions of years rather than just occasionally. A stable tilt means predictable seasons. Predictable seasons mean consistent climate zones. Consistent climate zones mean life can actually plan ahead, evolutionarily speaking. The moon acts as a gravitational anchor for that tilt. Without the moon's stabilizing influence, computer models suggest Earth's axial tilt could wander chaotically, anywhere from nearly 0 degrees to over 85 degrees, over astronomical timescales. 0 degrees means almost no seasons at all, a uniform gray band of moderate temperatures around the equator, and frozen, sunless poles that never see direct light. 85 degrees is the other flavor of catastrophe. At that tilt, the poles point almost directly at the sun at different points in the year. Seasonal swings become almost incomprehensible. Summer at the poles would mean months of direct overhead sunlight. Winters would be months of total darkness and cold that makes current Antarctica look like a spa. Ice sheets would grow and collapse repeatedly, radically. Climate would oscillate between extremes that make the ice ages look like a minor inconvenience. Now, this wandering tilt would not happen the moment the moon leaves. It would take a very long time, and some researchers argue Mars, which has no large stabilizing moon, is a decent preview of what this looks like. Mars's axial tilt has varied between about 10 degrees and 60 degrees over millions of years. The result is a planet whose climate history is marked by dramatic instability. We have found geological evidence that Mars once had liquid water. Where did it go? Some of it left due to atmospheric loss, but climate chaos from wobbling tilt did not help. Earth, with a moon, avoided that fate. Earth without one might not. Back on the biological side, the creatures most immediately affected by losing the moon would not be the ones you expect. Sea turtles navigate using the moon. Dung beetles use the Milky Way, but also orient using lunar light. Coral reefs synchronize their mass spawning events to the lunar cycle, one of the most precisely timed biological events on the planet, where billions of coral polyps release eggs and sperm simultaneously on specific nights after a full moon. Remove the moon, and that synchronization falls apart. The spawning becomes incoherent, fertilization rates drop, reef populations decline. And because coral reefs support roughly 25% of all marine species despite covering less than 1% of the ocean floor, that is a cascading problem of remarkable scale. Fish populations that feed on reef organisms decline. Larger predators that feed on those fish decline. And somewhere in a chain you did not expect, human fisheries that feed coastal communities start showing the strain. Meanwhile, the nights get darker. Permanently, dramatically darker. The moon provides enough reflected sunlight to cast shadows. Without it, nights would be lit only by stars and distant planets. Animals that hunt by moonlight lose their advantage. Animals that hide from predators during dark lunar phases lose that behavior's usefulness entirely. Nocturnal ecology reshapes itself over generations, and not cleanly. Darkness that once came reliably in cycles becomes permanent. It sounds almost peaceful until you realize what it does to ecosystems shaped by that reliable light-dark rhythm over hundreds of millions of years. And humans would not escape the psychological dimension of this. Ancient calendars, religious cycles, agricultural planting schedules, navigation, poetry, all of it is threaded through with the moon. That is not a scientific consequence, but it is a real one. Now here's the part worth sitting with. All of this is not science fiction. The moon is genuinely moving away from us right now. The process is just slow enough that no human lifetime will notice it. In about 600 million years, the moon will be far enough away that it will no longer be able to produce total solar eclipses because it will be too small in the sky to fully cover the sun. That is actually one of the first measurable losses. The rest of the consequences follow on geological timescales. But the physics is real, the biology is real, and the conclusions are consistent. The moon is not a passive decoration in the night sky. It is an active participant in making Earth the specific kind of planet it is. It steadies our tilt, slows our spin, drives our tides, times our biology, and lights our nights. Lose it gradually, and you do not lose just the moon. You lose the Earth that the moon helped create. If you found that unsettling in a good way, there is a lot more where that came from. Subscribe and keep watching.